Okay, so today now we will start with the introduction to the logical gates. There are a lot of logical gates. One is the inverter, AND gate, OR gate, NAND gate, NOR gate, XOR gate, exclusive NOR gates. We will study all of these gates in our this lecture, and then we'll see how can we draw the logical circuit and analyze the logical circuits. Okay, now these are the gate symbols. Okay, the first gate symbol, this gate, the first one is the AND gate. The second is the OR gate. This is the NOT gate. This is the NAND gate. This is the NOR gate, and the last one is the exclusive NOR gate. Okay. Now, if you look at any kind of a gate, so in any digital system design, okay, we have a black box. We have a black box, and we have some inputs or some output. If you look at the first function, so now input is what? A and B, and let's assume that the output is C. So now this is a function. This is a function. And can you see here? So can we write it like this? C is a function of what? A and B. Now C is a function of A and B. Now if you look at the first gate, so now we say, now we can say that this is an AND gate, in which what are the inputs? A and B. What is the output? C. So this is this C. Okay. Now if you look at A and B, so A and B, if you look at here, how many bits? How many bits? 2 bits. And the output is a single bit. The output is a single bit. Now if you look at A and B, there are 4 possible combinations. So now we are 4 possible combination for A and B. What are these possible combination? Yes, please. A and B. 0, 0, 0, 1, 1, 0, and 1, 1. And now we have a logical AND C, just the same. 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1. So this is a logical description of an AND gate. Now we have another gate, which is an inverter. So which is an inverter? So now we have, this is the logical symbol. So this inverter has a single input and a single output. Let's assume that the input is K and the output is L. How many possibilities are there for K? Yes, please. 2. What are these possibilities? 0 and 1. So what will be the value of L? 1 and 0. So we call this, okay, now this is called as a variable. So now L bar, we call this as L bar. L is now the invert of K. Okay, now how do we express C? Yes, please. C is equal to what? A dot B. A dot B. So C is an AND gate, which is A dot B. Okay, now if you look at here, if the input is 0, the output is 1. If the output is input is 1, the output is 0. Okay, when should we use an inverter? What is the application of the inverter gate? Ones complement. Very good. So now let's assume if we have an n bit number. So now we have an n bit number. So what will be the input? So any n bit number, and if we want to find the ones complement, so we want to find the one complement, and let's assume that this is number A3, B, A2, A1, and A0. How many bits? 4 bits. Okay, the output is C1, C2, C3, now we say C3, C2, C1, and C0. Okay, so this is a 4-bit number. This is a 4-bit number, and the output is also a 4-bit number. Okay, so now if we use this one inverter, second inverter, third inverter, and fourth inverter, to find the ones complement, to find the ones complement of a 4-bit number, to find the ones complement of a 4-bit number, how many inverter do we need? 4. Okay, so now the same problem that we want to solve. So let's assume that we have an n-bit number. We have an n-bit number. So now the input is now an n-bit number. So the input is, let's assume, a n minus 1, a n minus 2, blah blah blah, until a1 and a0. What will be the output? Yes, please. B0, then B1, and Bn minus 1 and then Bn minus 2 and blah blah blah. Got it? So can we write it like this? So Bn minus 1 is the invert of An minus 1 whole bar, An minus 2 bar, and then A1 bar, and then A0 bar. Okay, how many inverters do we require? N. So to find the ones complement, so we require N inverters, and this is inverter. This is called as a logical gate. So we need N inverter to find the ones complement. To find the ones complement of an N bit number, we need N inverter. Got it? Should we proceed? So application of inverter is a ones complement. This is the binary number. This is the ones complement. Okay. So now what is in this example? This A7. It's an 8-bit number. A7, A6, A5, A4, A3, A2, A1, and A0. And what is the output? Bn minus 1, Bn minus 2, B7, B6, B5, B4, B3, B2, B1, and B0. Should we proceed? Okay. Now we go to the other gate. It's a 2-input AND gate. So now the output. So 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1 is 1. This is a simple logical gate. Okay, now we can have a 2-input AND gate, we can have a 3-input AND gate, and we can have an input AND gate. Okay, now how many inputs are there for the AND gate here? 2 input. And now F1 is a 2-input AND gate, and this is a multi-input AND gate. Okay, so now let's assume we have now another AND gate. A1, A2, A3, AN. How many inputs are there? N inputs. Okay, N inputs. And now we have an AND gate, and the output is C. The output is C. So can we say that C is now a function of what? A1, A2 until AN. Okay, so if any of the input is 0, the output will be 0. If all inputs are 1, the output will be 1. Okay, so if any input is 0, so actually C will be equal to 0 if any of AI is equal to 0. Okay, and if C will be equal to 1 if all AI are equal to 1. And what is the range of I? What is the range of I? So actually now we start from A1. So 1 is smaller or equal to I, and smaller or equal to what? N. Got it? So now this is an N bit, the functionality of an N input AND gate. Should we proceed? Easy or difficult? Easy. Good. Okay, now this is the timing diagram. So now this is a timing diagram. So if you look at here, this is the timing diagram. So this is the waveform. This is a waveform. This is a discrete signal. Remember, it's a discrete signal. So okay, what is the initial value of A? 0. Then it become 1, then become 0, then become 1, 1, 1. And now if you say, now there are different time instant. During time t0, what is the value of A and B? 1, 1. What will be the output? 1. 0, 1, 0. Okay, so now if you look at it, this is 0, 1. So the output will make a transition from 1 to 0. Then we have 1, 0. The output is 0. 1, 1, 1, 0, 1, 0, 1, 0, 0, 1. 0. Any question? Should we proceed? Okay. Now, what is the application of an AND gate? So, okay, now this is a very important application of an AND gate. So, if you want to enable or disable a circuit, I will explain this with an example. So, to explain this, the application of an AND gate. So, first we need to understand the concept of a counter. What is a counter? Counter count the clock pulses. Counter clock pulses. Assume that we have a clock signal. So now this is a clock signal. There is a clock signal. Can you see here the clock signal? Then this is a clock signal. Okay. Now this is pulse number 1. Clock period 2, 3, 4, 5, 6, and 7, and it will continue on. Okay. Now the counter will count the number of pulses. What will be the value of counter at this point? 1. Then 2, then 3, then 4, then 5, then 6, and then 7. Got? So what does counter does? It count the number of pulses, and as we it will enable. Okay, but sometimes we would like to enable the counter and we would like to disable the counter. Okay, so now what we do instead. Okay, now this is signal A. This is signal A. Can you see here? This is signal number A. Okay, now if you put an AND gate and we put signal A, okay, and then the output is F, and we put an enable signal. What will be the function F? Yes, please. A dot E. Okay. Okay. Now instead of counting the signal A, we are now counting the signal F. Okay. Now there are two possibilities. Enable can be, if enable is equal to 0. If enable is equal to 0, what will be the value of F? 0. If enable is equal to 1 dot A. Because 1 A dot 1. So A dot B, it is actually A dot E. When E is equal to 1, it will be A dot 1, and A dot 1 is actually A. Got it? Okay, now we have this A signal. Okay, now assume that now we have an enable signal. At this point, what is the value of enable? 0. And then the enable signal becomes 1 here. So now enable is what? 0, and enable is here what? 1. Okay, now what will be the value of A? So because A 0 0 0, what will be the value of F? Yes, please. In all cases it will be 0. And then when enable is equal to 1, then it can calculate the clock pulses. Okay, now what will be the value of counter here? Counter will become 0, but here counter value will be what? 1, then 2, and then 3. So now this AND gate application is to enable or disable a circuit. When we want to enable a circuit, E will be 1, and if we want to disable a circuit, E will be 0. Got it? Okay, now the logical OR gate. So the logical OR gate, so if the output will be 1, the output will be 1 in any of the input is 1. Okay, 0 0 0 0 1, any one, output is 1. 1 0 1 1 1 out. So the output will be 0. Okay, think the output will be 0 if all of the input are 0. So the output is 0 if all of the input are 0, and the output will be 1 if any of the input is 1. So this is called as a logical OR, the logical OR. So okay, now we have two functions, F1. So now this F1 is a function of how many variables? 2 variables, and F2 is a function of many variables. It is a function of many variables. Okay, so now we will explain this with an example. Now if you look at here, now this is an OR gate, A, B, C, and F. How many inputs OR gate? It's a 3 input OR gate. Okay, now we have another OR gate, K, L, M, and N, J. It's a 4 input OR gate. So J is a function of K, L, M, and N. Okay, now there are two possibilities. Let's assume if the input is 0 0 0, what will be the output? 0. If the input is 0 1 1, output 1. If any input is 1, output will be 1. Okay, if the input is 1 0 1 1, output is 1. If the input is 0 0 0 and 0, output is 0. So if any of the input is 0, no, if all of the input are 0, the output is 0. If any of the input is 1, the output is 1. So this is the functionality of an OR gate. It's a 4 input OR gate. So if it's a 4 input OR gate, so what is J? J is now a function of K, L, M, and N. Okay, now if you look at this, how many possible combinations are there? 16. There are 16 possible combination, and for only, so there are 16 possible combination. What are these? 0 0 0 0, then 0 0 0 1, and blah 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 until 1 1 1 1. Okay, for the first entry it will be 0, and for the rest of the entries 1. Got it? So now this is the functionality of an OR gate. Okay, if we have a 5 input OR gate, how many possible combinations are there? 32. 32. So there will be 32 possible combination. For the first row, 0 0 0 0 0, the output will be 0, and for all of the remaining 31 combination, the output will be 1. Any question? Should we proceed? Good. Okay, now there's a 2 input OR gate, this is a multi input OR gate, and output is 1. The output is 1 if any input is 1. Got it? So now 1 1 1 0 1 1 1 0 1 1 1 1 0 1 1 1 0 1 0 1. Got it? Should we proceed? Any question? Okay, and 0 0, both input are 0, the output is 0. Okay, now what is the application of an OR gate? Now let's assume that you have a car. You have a car, and now we have 4 doors of the car. 4 doors of the car. Now we have this door 1, door 2, and door 3, and door 4. And now you know there is a symbol here, there's some kind of LED, red LED. Okay, now this is an LED symbol. Now you say, if this is 1, it means that any of the door is open. Let's assume if 0 0 0 0, what does it imply? All the door are closed. So what will be the value of LED? 0. And let's assume this is 0 1 1 0. It means door 2 and door 3 are open. What will be the value of LED? 1. Let's assume 0 0 0 1. Door 4 is open. Still the output will be 1. So this is an application of an OR gate. So if any of the door is open, it will give a logical signal 1. And if this is 1, it will ignore the other. Got it? So the output will be 1. So now this is an application of simple application of an OR gate. Okay, now we have a NAND gate. What is a NAND gate? So in NAND gate, we are using N stand for negative, and AND. So now actually this is an AND gate, and now this is the NAND gate, not negative, NAND gate. So this is a NAND gate. Okay, now if you look at the okay, now it's a very important concept, and please you need to remember this concept. It's important. This is called as a duality principle. This is called as a duality principle. Okay, now if you look at here, so now this is an, which gate is this? NAND gate. How many inputs? 2 inputs. So this is equivalent to, this one is equivalent to, we are using an AND gate, and after the AND gate we are using an inverter. Got it? So now we have A and B. How many possible combinations are there? 4. So now if you look at here, so now here it will be A, B. So now can you see here, this one is F1. What is F1? F1 is equal to A dot B. Okay, and what about invert? What is F2? F2 is what? F1 bar. F1 bar is equal to AB whole bar. AB whole bar. So now we have AB, what are 0 0 0 1 1 0 and 1 1. What will be the value of F1, which is an AND gate? What will be the value of F1? 0 0 0 1. What will be the value of F2, which 1 1 1 0. Got it? So now this is F2, which is actually the AB whole bar. Please remember that this NAND gate is equal to negative OR gate. Can you see here, the bubble is on the output or the input? Output. If you want to push the bubble to the input, into the input, so it will become a negative OR gate. So this, when we want to push this bubble to the input, so now we want to push this bubble to the input, it will become a negative OR gate. So now what we have now that this is a bubble. Bubble means an inverter. Now let's do, this is A, and now this is what? B. What is your output? F. Got it? This is equivalent to what? An inverter, again an inverter, and then what? OR gate. So now this is A, and now this is B. What will it become? A bar and this B bar. So we can write for the OR gate, we say A bar plus B bar. Okay, now what will be, can you see here? Okay, so now this is A dot B, and this is A dot B whole bar. Okay, now we want to compute what? A bar. What will be the value of A bar? Yes, please help me. So this is A, and now this is the invert of A. So this is 0, 1, then 1, then 0, and then 0. Now we want to compute B bar. What will be the value of B bar? 1, 0, 1, 0. Okay, now we want to compute this. This was F. This one is F1. This one is F2, and let's assume this is F3. So now this is F3. So F3 is equal to A bar. So F3 is equal to A bar or B bar. So now what we are doing? So we are computing this, and we are taking OR. What about this? 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0. Okay, so if you look at here, so now we can say that these two functions are same or different? Same. So actually the NAND gate is nothing but it's equal to a negative OR gate. So if we say, okay, now we have another example. Assume that, okay, now if we say this is a NAND gate, K, L, M and N, and the output is P. Okay, the output is P. P is a function of how many variables? 4. P is a function. If you want to push the bubble to the input, what will it become? It will become negative OR gate. So P is equivalent to, it will become a negative OR gate. So the bubble will push here. So now this is K, and then L, there's M, and then N. So what is P? P is equal to, so we can say P is equal to what? K dot L dot M dot N whole bar. This is equal to, P is equal to plus L bar plus M bar plus N bar. So this is called as the duality principle, and in which we can convert a NAND gate into a negative OR gate by pushing the bubble from the output to the input. So when we push the bubble from the output to the input, the AND gate will become an OR gate, and the bubble will be pushed to the input. Yes, please.
So what's the difference between if we make the result of the OR gate negative?
No, the output is same. The output is same, but the implementation is different.
I mean the negative OR gate.
Uh-huh.
Difference between if we the normal OR gate.
Yeah.
Output of the normal OR gate.
But so if you say, so okay, now if you look at here, so, okay, can you see here? Please look at here. Okay, so this gate and this gate functionality is same or different? Same. So it means these are two different implementation of the same function. This is the implementation. You got it? I will explain this with another example. Assume you're hungry, okay, and then you eat rice, and you're hungry, you eat burger. Okay, both of you have solved the same problem, like fill your tummy, but you ate in burger, you ate. So now the same thing in programming. If you remember, you can solve a program using different methods. We can solve the program using algorithm 1 or algorithm 2. So both algorithms are different, but they solve the same problem. So this is called as the, so now we can say we have two different implementation and they solve the same function. You got it now? I think that you understood this thing. So now it solves the same problem. So a NAND gate is equal to a negative OR gate. Again, so now if you look at here, so if you say A dot B whole bar, so A dot B whole bar is equal to A bar plus B bar, and the same concept can be expanded. So these two functions are these gate equivalent or not equivalent? They are equivalent.
So I mean, what is the difference between this one and A plus B whole bar?
They are same.
Same thing.
They are same thing. The output of both is same. So A B, huh?
A plus B, not A dot B.
A plus B.
He's
one up.
asking what's the difference between a normal OR gate and a negative OR gate.
Okay, so now, okay, in a normal OR gate, there are no bubbles here. So this function is what? A plus B. Let's assume if you have this OR gate, Y and G. How can we write expression?
Y plus G.
Y plus G. Got it? And then we have this A bar plus B bar. Are they same or different? They are different, and we can prove it. Why? Okay, now let's assume if you have this thing, which one? This is a F3. Now we want to implement F4, and F4 is actually this A and B and F4. How can we compute F4? Please look at A, B. 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. Okay, now we want to compare A, F4, which is the OR gate. So this is an OR gate. And now we want to, I'm now answering your question. Now we want to compute F3. What is this? F3, which is, are these functions same or different? Different. Since they are different, so how can you say that they are same? Got it? So now a negative OR gate is not equivalent to an OR gate. Okay? Okay, now we proceed further. Two input AND gate, multi input NAND gate. Okay, now 1 and 1, the output is 0. 1 and 1, 1, and we invert it. 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1. So when the output will be 0? When the output will be 0? If all the inputs, if all inputs are 1, the output will be 0. If all inputs are 1, the output will be 0. If any input is 0, the output is 1. Okay, now this is another example of the application of AND gate. Okay, now let's assume that we have now 3 different devices. Now in this example, assume that we have 3 different devices. So we have this, how many devices are there? D1, D2 and D3. And now we have an AND gate and we say the alarm. It will turn on the alarm. We assume that if, okay, now if Di is equal to 1, device is working. And if Di is equal to 0, it means device is faulty. Device is faulty. How many possible combinations are there? D1, D2 and D3. Yes, please. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. If all the input of 1, the output is 0. So there will be no alarm. Okay? All devices are faulty. 1, 1, 1, 1, 1, 1, 1. Okay, so now this can be used to detect a failure in the system. So if any of the device is failing, it means it's 0. When it's 0, okay, now in any input is 0. The input of the AND gate is what? 0. And then it will invert it and 1. So the alarm signal will be 1 if any of the input is 0. Got it? So now this is the functional description of the NAND gate. So now we have a NOR gate. Okay, NOR gate. So the same concept. So now we use the same duality principle and the same concept. So I'm rubbing this off. So I'm rubbing this off here. Now if you look at here, okay, now we have this. Please look at here. Now we have this A and B. What is F1 now? What is F1 now? Let's say if this is F5. F5 is what? No. Yes, A plus B what? Whole bar. A plus B whole bar. So this, okay, now this is a NOR gate, but if you want to convert into, if you want to push this bubble to the input, what should we do? This will become very good, negative AND gate. So we push the bubble, so it will become a negative AND gate. So now this is A and this is B, and what will now, okay, now this is F6. What is F6? A bar dot B bar. Got it. Okay, now if we say AB, so now we have this A bar and B bar. What will be the value of A bar? 1 1 0 0. What will be the value of B bar? 1 0 1 0. Now we want to compute F5. F5 is what? Now we want to compute A plus B. The OR of A and B. 0 0 0 0 1 1 1 0 1 1 1 1. Okay, now we want to compute F5, which is A plus B whole bar. We want to invert this. What will be the output? Yes, please. 1 0 0 0. Okay, now we want to compute A bar dot B bar. Now this is A bar. Now this is B bar. A bar B bar, and we want to AND it. 1 1 F6 1 1. So now we are considering 1 1 is 1 1 0 0 0 1 0 0 0 0. Are they same or different? So if we say, so now we have proved that F6 is equal to A bar dot B bar is equal to A plus B whole bar. So in general speaking, so we say, now let's assume if we have a 5 input, if we have a 5 input NOR gate, for instance, this is a NOR gate and these are the 5 inputs. Okay, so this is, let's assume C1, C2, C3, C4 and C5. What will be this output? Yes, please help me. C1 plus C2 plus C3 plus C4 plus C5 and then whole bar, and this one is equal to what? C1 bar. Okay, so now this will be, so now we are pushing the bubble from the output to what? The input. C1 bar dot C2 bar dot C3 bar dot C4 bar dot C5 bar. So this is equivalent to the negative OR gate, which is actually 1 2 3 4 5. This one is C1, this one is C2, C3, then C4 and then C5, which is actually your F7. So now this is F7. So F7 and now this is your F8. The F7 and F8 both are equivalent using the duality principle. So when we have a bubble on the output gate, so we will push this bubble to the input. Got it? And so if we have bubble, okay, now we have bubble of the NOR gate. When we push this bubble to the inputs, so the OR gate will become what? AND gate. And if we have a NAND gate, we have a NAND gate, and we want to push this bubble to the input, it will become negative OR gate. Got it? So this is how it works for the different logical gates. Okay, now, so we say A plus B whole bar is equal to A bar dot B bar. So this is the timing diagram of a 2 input NOR gate, 1 1 0 0 1 0 0. If you look at here, so we can say if all inputs are 0, the output is 1. If any input is 1, the output is 0. So now this is the logical description of a any n input or NOR gate. So now we have another gate. We call this as the XOR gate. XOR gate is also called as exclusive OR gate. Okay. Now we're going to have like a detailed analysis of this exclusive XOR gate. Okay. Now assume, okay, what are the inputs now? Okay, now this XOR gate, this is called as the XOR gate. So now we have a double sign XOR gate. So the input is A and B. And what is output? So we call this as A exclusive OR B. A exclusive OR B. Okay, now this A exclusive OR B, so now we have A and then B. Okay, and now we have A exclusive OR B. So this is 0 0 0 1 1 0 and 1 1. So it is performed just like a bit addition. 0 0 is what? 0 0 1 1 1 0 1 and 1 1 0. Okay, now this A exclusive OR B is equal to, so this A exclusive OR B is equal to A bar B or A B bar. Okay, now if we say what is now A bar and now what is B bar? Help me. What is the value of A bar? A bar 1 1 0 0. What is the value of B bar? 1 0 1 0. Okay, now we want to compute. Please, we want to compute. Okay, now can we say this one is F1, this one is F2?
This is A bar and B.
Yes, A bar and B. Yes, A bar B and A B bar. So okay, we want to compute A bar B. We want to compute F1. Okay, A bar. Look at the corresponding column. We want to compute A bar and what? B. So A bar dot B. So now this column 1 and 0 0 1 and 1 1 1 and 0 0 0 0. Okay, and then 0 1 0. Now we want to compute F2. What is F2? A dot B bar. Okay, now for A dot B bar, which column should we consider? A dot what? B bar. We need to consider 0 0 1 0 0 1 0, then 0 0 0 1 1 1 and then 1 0 0. Got it? And now we want to compute F. What is F? F1 plus F2. Now we want to take F1 and F2. We want to take in OR of this 0 0 0. So now this is actually we can call it, this is F. Let's assume this is F3 and this is now F4. This is F3 and now this is F4. Now we have an F4. What is F4? F4 is equal to, so can you say F4 is equal to F1 plus F2? So now there are two functions, F1 plus F2, 1 0 0 0 1 0 1 0 1 1 0 0 0. So are these expressions same or different? This one and this one are same. So you can say A exclusive OR B is equal to A bar B plus A B bar. Any question? Yes, please.
How do you add exclusive? Like there are
For exclusive OR, there are only two inputs. There is no exclusive OR with a 3 input. So exclusive OR is always a 2 input. That is not true. It's a very good question. Exclusive OR is a 2 input AND gate, 2 input gate. AND gate can be a 2 input, 3 input, 4 input, or multi input. NOR gate or NAND gate can be multi input, but exclusive OR only is a 2 input. Got it? So you cannot generalize the concept for the exclusive OR gate. It's a very good question. Okay, so okay, now we can say same inputs output is 0 and different inputs output is 1. So now A exclusive OR B. Now we have proved it or not? This one. A bar B, now we have proved it. So 1 1. Input is same or different? Same, 0. Different, 1. Same or different? Different. So same input. Okay, it can also be called as a bit addition. It will perform a bit addition, like just like a sum. Got it? Logical. So logical gate. This is called as exclusive NOR gate. Exclusive NOR gate. So now, as far as until now, we have studied which gate? Yes, please. Exclusive OR gate. Now we are studying another gate which is called as exclusive NOR gate. So in exclusive NOR gate, we do nothing but we just put an inverter at the end of the exclusive OR gate. So can you see here? So we put an inverter here, just like this is exclusive NOR gate. So we can say okay, now let's assume this function is F8. F8 is exclusive NOR gate. So we can say A, this one is the symbol for exclusive NOR gate. We can also write it like this. So A exclusive or B is actually A exclusive or B whole bar. A exclusive or B whole bar, and this one is equal to A B plus A bar B bar. So assume that this one is F8 and assume that this one is F9. So we want to compute F9. But to compute F9, we need to compute F, which is AB, and we need to compute A bar B bar, which is F11. So let's prove it. Let's prove it. Okay. Now we have, okay, now we have which function? We want to compute F8. Okay, exclusion OR gate is also an equality gate. An equality gate. If the inputs are same, if two inputs are same, the output will be 1. So same input or different inputs? Yes, please. Please. Same input, the output is what? 1. And different inputs? Output is 0. Same input. So same input. So now these are the same inputs. So this output is 1. And same input, the output is 1. And different inputs, the output is 0. Okay, now we want to compute what? F10. What is F10 now? Please help me. F10. F10 is what? AB. AB is nothing but an AND gate. So AB, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Now we need to compute F11. F11. What is F11 now? A bar, B bar. These two columns. 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 0. Now we need to compute F9. What is F9? F10 plus F11. So now F10 and F11. So this is an OR gate. 0, 1, 1, 0, 0, 0. Then and then 1. Same or different? Same. So now this F8. So this implies that F8 is equal to F9 and F8 is equal to A exclusive or B is equal to AB plus A bar B bar. Got it? Any question? Should we proceed? And the same question that you asked. So there is no 3 input exclusive NOR gate. The exclusive NOR gate is only a 2 input gate, and it's actually a comparator operation. It's a comparator. If you are comparing a bit by bit operation, if you want to compare 2 bit by bit, so if those bits are equal, the output will be 1. And if those bits are not equal, the output will be 0. If you look at all of the gates will lead to a Boolean expression. And for a Boolean expression, the output can either be a logical 1 or a logical 0. So the output of any gate, if you look at for all the gates, whether it's an AND gate, it's a NOR gate, it's exclusive OR gate, exclusive NOR gate, for all of the gates, the output can either be a logical 1, which is actually true, or a logical 0, which is actually false. Any question? Should we proceed? Okay, now we go further. So now this is the A bar B bar, and we have derived this expression. Same or different? 1, 1. Same. 1. Same or different? 0. So for same, the output is 1, and for different, the output is 0. Okay, now we want to draw some logical circuits. Now we can use a combination of different logical gate to find a logical expression. So now assume that we have this x, y, z bar. Should I write this off? Okay, so now assume that we want to find a logical, now we have a logical expression, and then we can derive. So now if you look at here, so now there is a logical expression. So what is f1? F1 is a function. So f1 is x, y, z bar. X, y, z bar. Can we write something like this? So f1 is equal to x, y, k. Can you write? What is now k? Z bar. So x dot y dot k is what? X, y dot y dot k. So it is a 3 input AND gate. So we have a 3 input AND gate whose input is what? X, then y, and then k, and the output is what? F1. But if you look at k is actually Z bar. So now we use an inverter here, and now this is. So now we have now a logical expression x, y, z bar, and now we want to transform this into a gate. So this is an equivalent gate. Got it? Should we proceed? Okay. Now we have another function. Now we have another function, this function, And if you look at this function, so now we want to compute what? F2. So F2 is equal to x plus y bar z. So can we write it like this? X is equal to x plus p z. And what is p? Y bar. So we can also write it like this. Please, we can also say. So we can also derive this x plus p z. Okay. So x plus y bar. This is x plus p z. So now we can say x plus m. And what is m now? PG. What is, which gate is this? OR gate. OR gate. So now we have an OR gate. What is the first input? X. What is the second input? M. But if you look at M and AND gate, what are the inputs? P and Z. But if you look at P, what is P? Y bar. What do we need here? Got it? So now this is how do you derive an expression, and when you will be experienced, you can do it directly. It's when you will experience. So if we look at here, so now this is okay. Now this is y bar. So y bar. So there is inverter before. Got it? Okay. Now if you look at this expression, x y bar. So now there are two literals. Now if you look at this expression, and if you look at this expression, so x y bar plus x bar z. So can we write it like this? P plus Q. P plus Q. Okay. Now we can say, okay, now what is P? X y bar. What is Q? X bar z. So can we write it as x y bar? We can say x m. What is m? Y bar. And then x bar z. So T Z. So okay, now what do you do? P plus Q, which gate? OR gate. Now we have an OR gate, and let's assume this is F2. So this F2 is now P plus Q. But if you look at P, which is XM, and XM is what? AND gate. This is X and M, and now Q is what? TZ. T and Z. But if you look at M y bar, y, so M is what? Y bar, and then what is this? Which variable? X. X bar is T. So now we can have
No, sir. T is X bar.
T is what?
X bar.
Okay, T is X bar. Yes, here. X. So now we can have an X and X here. And now this is the whole logical expression. Now we have this logical expression, and now we have transformed this into gates. Got it? Okay. Any question? Should we proceed? Good. Fast or slow? Fast? Yeah. Okay. Now, if you look at here, draw a logical circuit. Think. Draw a logical circuit of this. Yes, please. Yeah.
What is this line from X?
Which one?
The last one.
This one?
Yeah.
This one is X. X is same. This is also X. This is also X.
We should connect them together.
Yes, we can connect them together. When both signals are same, we connect them together. Got it? So these two signals are same. It's a very good question. So you have to. Okay. Now, if you look at here. Okay. Now draw a logical circuit. Okay. BD plus BE plus D bar F. Got it? So can we say what is this? Let's assume this one is F1. This one is what? F2. This one is F3. What do we need? OR gate. How many input OR gate? 3 input. So we need a 3 input OR gate. And this output is, let's assume this is Fj. The output is Fj. And the input is what? Yes, please help me. F1, F2, and F3. If you look at F1, F1 is BD. So F1 is B dot D, which is the AND. What is F2? B. Okay, now the same concept. B. We are connecting. This is B, and then what? E. What about F3? D bar F. D bar. Now we have D here. Can you see here? D, and now we want to invert it. What is this? D bar, and then F. Am I still first? Good. Okay. So now VD. Now what is this F2? BE, and F3. D bar F, and this one is. Any question? Should we proceed? And the same thing. If you look, please look at here. Think. Just think. How many input OR gate we require? 4 input OR gate. And then we need what? 3 input AND gate. Then 3 input AND gate. Then 3 input AND gate. And then 3 input AND gate. And we also need 4 inverters. Why? 1 inverter for what? A bar. 1 inverter for what? B bar. 1 inverter for what? C bar. And 1 inverter for E. Got it? Okay. So now you can do these tasks. So these are the tasks. Okay. Now. Okay. Now these are some basic theorems of Boolean algebra. So now we can say what is a null operator. So now what is a null operator? So now these are the expression for a Boolean algebra. Okay, x plus 1 is equal to 1. X plus 1. So x plus 1 is equal to 1. How we prove it? Okay, now there are 2 possibilities. So x can have a value of either a logical 0 or a logical 1. So there are 2 possibilities. And now we want to compute f. F is an expression. Okay, so now f is equal to x plus 1. Okay, so now we have 1 here and 1 here. Okay, now x plus 1 is OR gate. So what is f? 1 and 0. 1. 1 and 1. 1. So f is always equal to 1. Got it? Okay, now if we say f is equal to x dot 0, anything multiplied by 0 is what? 0. So f is actually f. This is f1 and this is f2. So okay, so f2 is equal to 0. So now this is called as the null element for the plus and the null element for the dot. Yes, please.
F2 can be 1.
Which one?
F2. It could be 1.
No, F2 cannot be 1.
No. For F2, there x can be 1.
X can be 1 or 0, but when we AND it with 0, output is 0. 0, 0 is 0. This is because we are ANDing it. Okay, now in F2 and F2, what we are doing? So now we are ANDing it with what? We are ANDing it with this 0 and 0. 0, 0. 0. 0, 1. 0. Output is 0. Anything AND with 0. So what's the property of an AND gate? So the property of an AND gate, we have x, now we have 0. What will be the output? 0. If any input is 0, the output will be 0. It will ignore. Either it is 0 or 1, doesn't matter. In both cases, the output will be what? 0. And now we have an OR gate, and now we have a 1, and now we have x. X can be 0 or 1. 1, 0. 1, 1, 1. 1 in both cases. So this is called as the null element. Got it? Okay. Now we have another theorem. We call this as the involution theorem. So we say x double bar. X double bar. Can we write it like this? X is equal to f y bar. What is y? Y is now x bar. Okay, and then y is equal to x bar. So now if we have x double bar, so now let's assume we have an x. We have an x. Okay, now if you put an inverter here, what is this expression? X bar. And we put another inverter here. What is this? X bar double bar. If this is 0, what will it become? 1, and it become 0, and this is 1, 0, and then 1. So this x double bar is nothing but x bar. X double bar is equal to x, not x bar. Got it? Okay. Now, if we have, okay, now I have this question. This is a tricky question. Please, if you, what is equal to y bar bar bar? Because y double bar is equal to y, and then it's y bar. Okay, so now this is an involution theorem, and you can recursively apply this involution theorem to lead to a simplified expression. And now this is the De Morgan theorem, the same thing we studied. Okay, which gate is this? Which gate? NOR gate. NOR gate. And which gate is this? Negative AND gate. Which gate is this? NAND gate. And this gate is negative AND gate. Got it? So now, okay, I will, for someone who is like confused, I will explain it again, no problem. It doesn't matter. I can explain it multiple times. And when we repeat it, so typically the concepts are, so if we say x plus y whole bar, so x plus y whole bar is equal to x bar y bar. So x plus y, OR gate, and then we put an inverter. This is an OR gate. So x plus y. So this one is F1. So this one is F1, and it's actually, so we put the bubble to the input side. So what is this? F2. So this F1 is what? Yes, please. X plus y whole bar. And what about F2? X bar what? Dot y bar. So when we have a bar on the whole, yes, please. Yeah, bubble is an inverter. Yes. Okay. So bubble is an inverter. So F2 is equal to x bar dot y bar, and we explained. So this is called as De Morgan's theory. And then that's for us the further thing. Xy whole bar, which is actually F3, is equal to F4, which is actually x bar plus y bar. So xy whole bar. So now this is xy whole bar. This is a NAND gate. So this is x and this is y, and this is your F3. This is xy and then whole bar on this. And when we put it, so we push the bubble on the input side. So now we have a negative OR gate, and then now x and y. And what is the output now? X bar plus y bar, which is actually what? F4. So F3 is equal to F4. So now this is F3 is equal to F4, and this is F1, and this is F2. Got it? Any question? Should we proceed? Okay, now we have, okay, now we want to analyze this logical circuit. So what is the Boolean expression of F4? Yes, please. What will be the output here? A bar, B bar. So A bar, B bar, and A bar. Can you see here? A bar, B bar. Okay. And then what will be the output of this? Yes, please. A bar, B bar plus what? Plus C. So A bar, B bar plus C. A bar, B bar plus C. Okay. Now what will be the output of F4? A bar, B bar plus C whole bar. Okay, now what we do? So it's a very important concept. And this concept will be like used many times. So if you say, should I rub this off? Yes. Okay, now we say, so now we have a logical function. So please think. So any Boolean function can be implemented using different methods. So now F4 is a Boolean function. This F4 is a Boolean function. It will either be a logical 1, or this F4 will be what? A logical 1 or a logical 0. Okay, now how do we calculate F4? So now we have an F4 here. What is the expression of F4? Yes, please. A bar, B bar plus C whole bar. Got it? So now this is the whole expression for F4. Okay, now if you look at the logical circuit, now we have the logical circuit. So the logical circuit is something look like this. So now we have the logical circuit, which is actually what? A bar what? A bar, B bar, and then C, and then F4. Okay, now what we want to do, and now this is very important concept. So you can you write it like this? F4 is equal to A bar B bar plus C whole bar. Okay, so can we write something like this? A bar B bar is equal to J plus C whole bar. Can I write? Now what is J? A bar B bar. We apply the De Morgan's theorem. When we apply the De Morgan's theorem, so actually the bubble is on the output. Now we push the bubble to the input side. How can we write it? J bar dot C bar. Got it? Okay. Now J bar dot C bar. But what is J now? A bar B bar. So can we say, okay, now this is J. So now J is A bar B bar and then whole bar. Okay, dot what? C bar. Okay, now we apply the De Morgan theorem. So can we write it like this? So A, there is dot. Dot will be replaced by what? Plus. So now we put a parenthesis here, just like for the sake. So now we have a parenthesis here. So what will we do? A bar, it will become what? A double bar. Dot will be replaced by what? Plus. And then what? Got it? And A double bar is what? A plus B dot C bar. Okay. Now, if you want to have the logical expression for this, what it becomes? So now it becomes what? This one is OR gate. Okay. So now this is F4, and let's assume this is F5. Okay. So now F5 is what? A plus B A plus B dot what? Got it? Okay. Now, if you look at here, we have different implementation of the same function. We have different implementation of the same function. Okay. In this implementation, can you look at this implementation? How many gates do we require? 3. How many gates? 1, 2, and 3. How many gates? 3 gates. Which implementation is better? Which one? Why? No, the same thing. There are 3 gates and 3 gates. The cost is same. 1 OR gate, 1 AND gate, 1 NOT. The cost is same. Yes. Okay. So if you look at here, please look at here. Assume we have some delay. This gate has a delay of D1. This gate has a delay of what? D2. This gate has a delay of D3. So what will be the total delay? Plus D2 plus D3. Now in this case, we have a delay of D1, and now we have a delay of what? D2. So what is the delay one? So delay one is D1 plus D2, and now so this D1 is for the AND gate, and D2 is for the OR gate, and D3 is for what? Inverter. We have 2 paths. This is path number 1, and this one is path number 2. So path 1 has a delay. So path 1 has a delay of what? Path 1, D1 plus D2, and path 2 has a delay of what? D3. So the critical delay here is less or more? Less. And here the critical delay is more. So now we have 2 different implementation of the same function. They are using the same gates, but in that case, this path and this path, they are computing it in parallel. When they are computing in parallel, this implementation is much better. Okay, now we have also another implementation. If you look at here, so can we see here? So we can also derive this expression. So we can say A plus B. Now we have A plus B. Now we have, this is F4. Now this is F5. So A plus B dot C bar. Can we write like this? A C bar plus what? B C bar. Okay. So we need an OR gate. We need an OR gate. Then we need 2 AND gates because we have plus. Okay. Now we need A and then what? A C bar, and then B C bar. How many gates are required? 1, 2, 3, 4, and 5. Which implementation is better? 1, 2, or 3? 2 is better. So we can have different implementation. We can have different implementation of the same function which has the same or equivalent output, but each of these implementation may have different characteristics. I will explain this again with the same example. Let's assume you're hungry, you eat burger, you eat pizza, and you eat rice. Okay, what is the objective? Fill the tummy. But this implementation, rice is more healthy, and these are unhealthy. This is unhealthy food. So now it depends on the scenario. So we can have different implementation of the same function, and now we can have different implementation of the same function, and then we can deduce that which implementation is better. This implementation can be in terms of the gate cost. So what is the gate cost here? So in this case, we need one OR gate, one AND gate, and one inverter. In this implementation, we need one OR gate, one AND gate, and one gate. The costs are both the same. But then we see the critical path. So the critical path of this contains of 2 gates, and the critical path consists of how many gates? 3 gates. So this implementation is much better. And this implementation is not good in terms of cost. How many gates are required? 5. One OR gate, 2 input AND gate, and so actually when we want to fabricate, so now we have chips. We have a big integrated circuit chips, and this chip consists of millions and millions of gates. So if you have this computer, this mobile, so in this mobile, so these are the processor. All the processor are implemented using gates, and now we have millions and millions of these gates, and this is not one gate, not 2 gates. How many gates? Millions, and in some implementation there are billion. So if the processor is complex like this, the desktop processor, the dual core or core to do, maybe it contains billions and billions of these gates, and million and million of these gates, and every gate has a different function. So now we can design more content, more complex. Initially I was going too fast because my objective was to have very, very good implementation in designing very complex system, but most of the students are not happy with the pace. That's the reason that I slowed up my pace. I wanted to give you a lot of, to design very complex circuits. This was my initially objective. So if you want to solve very complex circuit, you can come to me for like and separate. So now this is the different implementation. So now what is the Boolean expression of F5? Yes, please. XY plus YZ. What is this? XY. What is this? YZ. Then plus YZ. Okay. So now this is like the thing. So now if you look at the universal gate, NAND gate. Okay. So now these are 2 universal gates. We call this as the universal gate, NAND gate or NOR gate. NAND gate and NOR gates are called as the universal gates. Your NAND gates and NOR gate are called as universal gates. Okay. Now how can we say that this is a universal gate? We can implement any kind of gates with the NAND gate, either the NAND gate or the NOR gate. I will explain this with an example. Can you see here which function we are implementing now? Can you see here? XY. What is Z? XY whole bar. XY whole bar, and then X bar plus Y bar. This is the De Morgan's theorem that we apply. Okay. Now, if we see here, now we can also implement an inverter here. Okay. Now we have a NAND gate. Typically, the NAND gate is A, B, and this is NAND gate. What is output F? What is F now? Yes, please help me. A dot B whole bar. But if we make something like this, instead of A and B, we put A and A. They are the same signal. Okay. And now this is, let's assume F2. What is F2? A dot A whole bar. And what is A dot A? A dot A is actually A. Why A dot A is A? Okay. Now there are 2 possibilities of A: 0 and 1. So what is A dot A? 0, 0. A dot A. This is A. 0, 0, 0, 0, 1, 1, 1, 1. So A dot A is equal to A. So this is A dot A whole bar, A dot A is what? A bar. So we can implement an inverter using a NAND gate. We can implement what? An inverter using the AND gate by putting the two of the inputs are same. Yes, please. Which one? Because this is a universal gate. If we want to transform all of the gates into the form of the NAND gate, we can do that. Got it? Why? Because NAND gate and NOR gate are universal gate. Okay, if you have only gates that are available, let's assume you have one gate, only one, and that is one NAND gate. You don't have any inverter. You can use it as an inverter. Got it? So now, in this case, we don't have any gate available. The only gate available is what? NAND gate, and we are implementing. So we are implementing an inverter using a NAND gate. Assume that inverter is not available. Got it? That's the reason that we call this as an inverter. So this is called as idempotency. X dot X is what? X, and this is X whole bar. Okay, now we want to implement an AND gate using a NAND gate. Okay, so now we want to implement an AND gate. We want to implement an AND gate. How can we implement an AND gate? Can you see here? AND gate. We want to implement an AND gate. So this is equivalent to what? Because we can only use. Got it? Okay, now this is a bubble and this bubble. This bubble will what? Cancel out. This is, let's assume this is A and this is A double bar, A bar and A double bar. This will cancel out. So can we write it like this? So now this is AB. So this AB is, let's assume F. This is again F because we are putting double inverter. So now we have this A and B. And now how can we implement an inverter using a NAND gate? Use another NAND gate, and the two inputs are what? Same, and this is what? F. So now this is, can you see here, what is this? AB whole bar, and now we have AB what? Whole bar, and then AB whole bar, but then this F is what? F is equal to what? AB whole bar, and then AB whole bar, and then whole bar, and this is some, let's assume this is F1. Assume this is F1. So we have F1 dot F1 whole bar. Okay, so F1 dot F1. What is F1 dot F1? F1. Okay, now and then double bar. So this is F1 is actually, F1 is what? AB whole bar. So it will become F1 and F1. We can write it once. AB bar whole bar, and now this whole bar is from here, and AB double bar is what? AB, and now we have converted an AND gate into two. How many two NOR gates are required? Two NOR. So now we will have different implementation. It's all for today. Thank you very much. And then I will mark in attendance. Attendance is very important.